Somewhere at the very edge of everything the sun still governs, a signal that had been silent for 5 months suddenly came back to life. And when engineers at NASA finally decoded it, what it was reporting from that boundary made several of them stop and read the numbers twice. Not because the spacecraft had broken, not because it had drifted off course, because the region it was sitting in, a stretch of space every physics textbook described as cold, faint, and largely uneventful, was recording temperatures of nearly 50,000 degrees Celsius. That's hotter than the surface of most stars. And it was happening in a place where, according to every model built before this spacecraft got there, nothing that dramatic was supposed to be happening at all. This is not a plot device. This is a real, documented, peer-reviewed finding from Voyager 1, the oldest continuously operating spacecraft humanity has ever built, and it is one of several discoveries from the edge of our solar system that have quietly forced scientists to rewrite parts of what they thought they understood about where our neighborhood ends and the rest of the galaxy begins. Some of these findings involve heat that shouldn't be there. Some involve magnetic fields that shouldn't line up the way they do. And one involves a signal that has been humming continuously for years that scientists still can't fully explain. None of it is fiction. All of it is sitting in publicly available NASA statements and published research. And all of it comes from a machine that was only ever supposed to last 5 years, and is now, in 2026, still transmitting from farther away than any human-made object has ever been. To understand how strange these findings really are, you first need to understand where they're coming from, and why nothing had ever measured this place directly before. Voyager 1 launched from Kennedy Space Center on September 5th, 1977. Its assignment on paper was almost humble. Fly past Jupiter, fly past Saturn, take some photographs, gather some measurements, and then go quiet sometime around 1981. The engineers who built it were focused on storms in Jupiter's atmosphere and the rings of Saturn. Nobody on that team was planning for a machine that would still be reporting data from interstellar space nearly 50 years later. But Voyager 1 used the gravity of Jupiter and Saturn the way a slingshot uses tension, picking up speed with every pass, and it simply never stopped moving. By the late 1980s, it had already become the most distant object our species had ever launched. And in August of 2012, 35 years after liftoff, it crossed a boundary called the heliopause, becoming the first spacecraft in history to physically leave the solar system and keep transmitting from beyond it. Picture the sun not just as a source of light and heat, but as the center of an enormous bubble. It constantly releases a stream of charged particles called the solar wind, and that wind blows outward in every direction until it finally runs out of strength and meets the pressure of the interstellar medium, the ancient material that fills the space between star systems. The point where those two forces balance is the heliopause. Everything inside it belongs to our solar system. Everything outside it belongs to something else entirely. When Voyager 1 crossed that line in 2012, it did something no probe, no telescope, and no mathematical model had ever done before. It put a working scientific instrument physically inside the space between the stars, and let it start reporting back what that environment actually looks like from the inside, rather than what it was assumed to look like from 186 million miles away on Earth. That's where the first genuinely strange finding comes in, and it starts with temperature. For decades before Voyager 1 reached the heliopause, physicists had built careful models predicting what the transition zone at the edge of the solar system should feel like. The general expectation was a gradual, relatively gentle handoff, the solar wind slowly losing strength, the interstellar medium slowly gaining influence, a bit like a river gradually widening and slowing as it approaches the sea. What Voyager 1, and later its twin Voyager 2, actually measured was nothing like that. Instruments on both spacecraft recorded plasma temperatures at the boundary between 30,000 and 50,000 Kelvin, roughly 54,000 to 90,000 degrees Fahrenheit. Researchers and science writers have since taken to calling this region, informally, the Wall of Fire. It's an evocative nickname, but it's worth being precise about what it actually means, because the honest version of this finding is almost stranger than the dramatic one. This isn't fire in any conventional sense. There's no combustion, no flame, nothing burning. What's happening is that individual charged particles in this region are moving at extremely high speeds, and temperature, in physics, is fundamentally a measure of how fast particles are moving, not how much heat they could transfer to something sitting among them. Because the region is so sparse, with particles spread unbelievably thin across billions of miles of space, there simply aren't enough of them colliding with the spacecraft to transfer any meaningful heat. Voyager 1 and Voyager 2 both passed directly through a measured plasma temperature comparable to conditions near the surface of a star, and neither one so much as warmed up. That's the part that should genuinely surprise you, more than any exaggerated headline could. A region of space that looks, on paper, hot enough to vaporize anything that enters it, and a 50-year-old spacecraft with 1970s electronics sailed straight through it without a scratch, because the particles were too sparse to matter physically, even though their individual speeds were real, measured, and extraordinarily high. It's a reminder that some of the strangest things in the universe aren't supernatural mysteries. They're just physics behaving in ways our everyday intuition, built entirely on Earth's thick atmosphere, was never equipped to expect. The second finding is about magnetism, and it might be even harder to reconcile with what scientists assumed going in. Before Voyager 1 crossed the heliopause, one of the standard predictions was that the magnetic field environment on either side of that boundary should be dramatically different. Inside the bubble, the sun's own magnetic field, carried outward by the solar wind. Outside the bubble, a completely separate magnetic field generated by the broader structure of the galaxy itself. Two distinct magnetic systems from two entirely different sources that should meet at the boundary and diverge sharply. That's not what either spacecraft found. Voyager 1's magnetometer recorded that the magnetic field just beyond the heliopause pointed in almost the same direction as the magnetic field inside it. With only one data point, researchers couldn't be sure whether that was a genuine pattern or simply a coincidence tied to Voyager 1's specific location along the boundary. Then, in 2018, Voyager 2 crossed the heliopause at a completely different location, on the opposite side of the solar system, and its magnetometer recorded the exact same thing. Two independent measurements, taken years apart, from two different points along an enormous boundary, both showing that the sun's magnetic field and the galaxy's magnetic field are, in this region, essentially parallel to each other. NASA's own science communications team described this directly in a statement following the analysis, noting that the observation from Voyager 2 confirmed what had initially looked like a surprising, possibly coincidental result from Voyager 1. That confirmation matters. It means our solar system isn't sealed off from the rest of the galaxy the way earlier models assumed. There appears to be a real structural connection between the magnetic environment we live inside and the magnetic environment of interstellar space itself, one that current theory still hasn't fully explained. Some researchers have pointed to a related process called magnetic reconnection, a phenomenon where field lines from different sources interact, rearrange, and release energy as a possible piece of the explanation. But this remains an active area of research rather than a settled answer, and that's worth being honest about rather than dressing it up as a bigger mystery than it currently is. The third piece of the story is the one that has stayed unresolved the longest, and it may be the strangest of all because it isn't a single measurement. It's something that has been happening continuously for years without stopping. Starting in 2017, Voyager 1's plasma wave instrument began detecting a persistent narrowband signal in the plasma surrounding it, something researchers have described as a faint but steady hum. This wasn't a single spike that could be written off as a sensor glitch or a brief anomaly. It has shown up year after year, tracked continuously across a stretch of interstellar space more than 900 million miles wide, roughly 10 times the distance between the Earth and the Sun. A team of researchers analyzed years of this data and published their conclusions in the journal Nature Astronomy, describing interstellar space as turbulent and structured in ways that decades of earlier models, built entirely from telescopes and equations on Earth, had simply never predicted. Not empty, not calm, active with a kind of physical texture that nobody had a way to directly observe until an instrument was finally sitting inside it. Here's the honest part of this story, the part that separates a real open question from manufactured suspense. Scientists studying this persistent signal have narrowed the possible explanations down to two, and they genuinely don't yet know which one is correct. The first possibility is that this is ordinary thermally excited plasma oscillation, the natural vibration of charged particles interacting with their surroundings. That would still be a meaningful discovery, but it would fit within existing physical frameworks without requiring anything to be torn up and rebuilt. The second possibility is something called quasi-thermal noise, a distinct physical mechanism that would carry information about the density and temperature of interstellar plasma in a subtly different way, one that would require real revisions to existing models of the interstellar medium. Telling these two explanations apart requires either more data from Voyager 1 itself, or a new mission built specifically to study interstellar space, with instruments designed for exactly this kind of measurement. No such mission currently exists, and no such mission is currently funded. If one were designed, built, and launched starting today, it wouldn't reach the heliopause for at least another 25 years. Which means whatever the true answer is, Voyager 1's own data may be the closest thing we have to it for a very long time. There's a fourth thread to this story, one that connects the science directly to the fragile, aging hardware that's still making all of this possible, and it involves a moment in 2023 that came dangerously close to ending the mission entirely. For 5 months that year, Voyager 1 continued transmitting a signal, but what it sent back was corrupted, unreadable, a stream of scrambled data that engineers at the Jet Propulsion Laboratory, after decades of experience reading everything this spacecraft had ever sent, simply could not decode. The cause once identified, turned out to be a single memory chip inside the spacecraft's flight data system that had physically degraded after nearly 5 decades of exposure to cosmic radiation. One small component, roughly the size of a fraction of an inch, had quietly failed, corrupting the section of software responsible for formatting and transmitting scientific data. There was no possibility of a repair mission. The component was over 15 billion miles away, and even a radio signal moving at the speed of light took about 22 hours to reach the spacecraft, with another 22 hours required for any response to come back. Every single diagnostic step in that recovery effort took a minimum of about 44 hours to complete, and every one of them carried the risk that a single incorrect instruction sent across that distance could end the mission permanently with no chance of recovery. The team at JPL worked through that problem for months, methodically, under a level of pressure that most engineering situations never produce. They eventually determined that the corrupted code couldn't be repaired in place, but it could be relocated, split into smaller sections, and rewritten to function correctly from new locations in the spacecraft's available memory, then carefully reconnected to work as a whole again. By April of 2024, Voyager 1 was transmitting clean, complete, readable scientific data once more, and what it immediately resumed sending was more of that persistent, unexplained plasma signal, more evidence of the same structured turbulence in interstellar space that nobody had fully explained before the spacecraft went quiet, and that nobody has fully explained since. That resilience matters, because it's directly connected to what's happening to Voyager 1 right now in 2026, and why the next stretch of this mission may be one of its most consequential. Voyager 1 runs on a radioisotope thermoelectric generator, essentially a sealed container of decaying plutonium that converts heat into electricity as it breaks down. At launch, it produced roughly 470 watts. Today, after nearly 50 years, it produces roughly 250, and it loses about 4 watts every year, permanently, with no way to refuel or replace the source. In February of this year, during a routine calibration roll, a standard maneuver the team has performed many times over the decades, Voyager 1's power levels dropped further than expected. Rather than let the spacecraft's automatic safety systems handle the situation on their own, which would have meant a long, uncertain recovery process across that same 23-hour communication delay, engineers made the deliberate call to act first. In April, they permanently shut down the low-energy charge particles instrument, a device that had operated almost continuously since 1977. Of the 10 instrument packages Voyager 1 launched with, 7 have now gone silent. Every one of those decisions is final. There's no way to reach across 15 billion miles and physically switch anything back on. But the team hasn't stopped trying to buy more time. Engineers at JPL are currently testing a power restructuring procedure, informally nicknamed the Big Bang, designed to recover small amounts of electrical capacity currently being lost to inefficiency in the spacecraft's aging systems. Because any change to hardware this old carries real risk, they tested it first on Voyager 2, which has a slightly larger power margin, before attempting the same fix on Voyager 1 as early as this month. If it works, there's a genuine chance the instrument shut down in April could be switched back on, and the flow of new information about that unresolved plasma signal could continue a little longer than anyone expected just a year ago. There's also a milestone already fixed on the calendar, arriving regardless of how that repair attempt goes. On November the 18th, 2026, Voyager 1 will reach a distance of exactly 1 light day from Earth, roughly 16 billion miles. At that distance, a radio signal takes a full 24 hours just to arrive, and another 24 for a reply to come back. No human-made object has ever operated that far from home while still transmitting. Here's what I think is worth sitting with. More than any single dramatic number, what Voyager 1 has actually found out there isn't evidence of something supernatural, or something that breaks the laws of physics. It's evidence that the universe, even in the places we assumed were the simplest and quietest, tends to be more layered and more active than our models, built from a single vantage point on a small planet ever gave it credit for. A region hot enough to match a star's surface and yet harmless to the spacecraft passing through it. A magnetic boundary that was supposed to divide 2 separate systems, instead quietly linking them. A signal that has been humming steadily for nearly a decade, that 2 competing explanations are still fighting over, with no new mission on the way to settle the argument anytime soon. None of that needed exaggeration to be remarkable. It's already remarkable, exactly as it is, measured honestly, by a machine that was only ever supposed to last 5 years and is now closing in on 50. Somewhere out past the edge of everything the sun protects, that same machine is still moving, still transmitting, still carrying its golden record. The disk, holding greetings in 55 languages, the sound of rain and ocean waves and human laughter, a message assembled by a team led by Carl Sagan on the chance that someone, someday, finds it drifting through the dark and wonders where it came from. Whatever Voyager 1 still has left to teach us about that strange, humming boundary at the edge of our solar system, it's transmitting that answer right now, in real time, on a fading power supply, across a gap so wide that even light takes almost a full day to cross it. Whether it gets to finish that story before the silence comes isn't something anyone at NASA can promise. If you want to see how far it gets, that's worth sticking around for. Subscribe if you'd like to follow it.